In the summer of 1950, 4 physicists at a research lab in the New Mexico desert were walking to lunch, half joking about flying saucers, when one of them, according to the people who were there, stopped mid-sentence and asked a question nobody at the table could answer. It wasn't, "Do aliens exist?" That was the easy part. The hard part was this: if the galaxy is old enough and big enough and runs on the same physics everywhere, then somebody, somewhere, should already be here. Where is everybody? More than 70 years later, we've pointed instruments at more of the sky than that lunch table could have imagined, and catalogued thousands of planets nobody knew existed. The honest answer still hasn't changed. No signal, no structure, no visitor, no exception. And that's the strange part. The silence hasn't shrunk as the search has grown. It has held steady in a universe where the numbers say it shouldn't. Stay for this hour, because the explanation that survives contact with the evidence isn't the comfortable one. It has a name, a position on a timeline, and that position might sit closer to us than anyone wants to admit. Let's begin. Start with the story itself, because most people get it slightly wrong. The man who asked the question was Enrico Fermi, one of the physicists behind the first nuclear reactor. The lab was Los Alamos. The year was 1950, and Fermi never wrote the question down. He never published it, never turned it into a paper, never gave it a name. He died 4 years later. What survives is second-hand, recollections from the colleagues who were walking with him that day, written down years afterward, agreeing on the gist but not on every word. The phrase Fermi Paradox did not even appear in print until 1977, more than 2 decades after the lunch. The formal argument, the one with numbers and logic attached to it, was built later, mostly by an astronomer named Michael Hart in 1975, and extended by a cosmologist named Frank Tipler around 1980. That matters, because this whole hour is built on a habit of being precise about what we actually know versus what we've decided to believe. So let's be precise from the start. Nobody has a transcript of Fermi's exact words. What survives is a question, reconstructed by memory, that turned out to be sharper than anyone at that table understood in the moment. Here's the version of the question that actually holds up. Stripped of the anecdote, given how old the universe is and how many places there are for life to start, why does it look like we're the only ones who ever did? To feel the weight of that question, you need the scale underneath it. And the scale is almost impossible to hold in your head, honestly. So let's build it in stages instead of throwing numbers at you all at once. Our galaxy, the Milky Way, is generally estimated to hold somewhere in the range of 1 to 400 billion stars. Take the low end of that range, and it still means that for every person alive on Earth today, there are roughly 50 stars in our galaxy alone. Most of those stars are older than the Sunday, some are far older. Stars that were already burning for billions of years before our own solar system had finished forming. And the Milky Way is only one galaxy. Step back far enough, and the observable universe is currently thought to contain somewhere on the order of hundreds of billions of galaxies. Each one, on average, holding a comparable population of stars to our own. This hour is going to stay disciplined and keep almost the entire investigation focused on our own galaxy, because that's where the actual searches described in the chapters ahead have taken place, and because reasoning about a single galaxy honestly is hard enough without inflating the scale further. But it's worth letting that larger number sit in the background for a moment, because it changes how you should hear every claim about rarity that comes later in this hour. Even a process so improbable that it succeeds only once in every 100 billion attempts would still be expected to have happened many times over, somewhere across a universe this large. Rarity, at this scale, doesn't automatically mean uniqueness. It just changes how far apart the successes are likely to be spaced. The Milky Way itself is thought to be around 13 billion years old, which means it has existed for almost the entire history of the universe. the universe itself is about 13.8 billion years old, a figure that comes from measuring the leftover glow of the Big Bang and the rate at which everything is still moving apart. These aren't round numbers picked for convenience. They're the current best answers from independent lines of evidence that keep landing in the same place. It's worth being honest, too, that Earth itself did not start out anything like the calm, temperate world it is today. For roughly the first several 100 million years of its existence, the young solar system was a genuinely violent place, a period often called the era of heavy bombardment, during which the inner planets, Earth included, were still being struck repeatedly by leftover debris from the solar system's formation, some of the impacts large enough to have melted significant portions of the young planet's surface, or vaporized any early oceans outright. That's an important, sobering detail, because it means the window in which conditions were stable enough for the chemistry of life to even begin was itself narrower than 4.5 billion years suggests at first glance. And yet, as the next paragraph lays out, life's earliest traces still show up remarkably close behind that violent opening chapter, which, if anything, sharpens the puzzle rather than softening it. Life didn't need calm, uninterrupted conditions stretching back to the literal beginning. It got started about as soon as the bombardment eased enough to allow it. Now put a second number next to that one, the age of Earth, at roughly 4.5 billion years. And here's the detail that does the real work in this argument. Life on Earth did not take anywhere close to that entire span to get started. Some of the earliest chemical traces that many scientists interpret as evidence of biological activity date back to within the first few 100 million years after the planet had cooled enough to hold liquid water at all. That dating is genuinely contested. The rocks are ancient, altered, and hard to read, and serious researchers disagree about how early the earliest confirmed life actually appears in the record. But even the cautious readings put recognizable life on Earth within the planet's first billion years, on a world that is, by any measure we have, an unremarkable rocky planet orbiting an unremarkable star in an unremarkable part of an unremarkable galaxy. There's a long tradition in astronomy behind that word ordinary, and it's worth naming because it's doing real work in this argument even when nobody says it out loud. Roughly 5 centuries ago, the idea that Earth wasn't the fixed center of the universe, just one more world orbiting an unremarkable star, was genuinely radical, and it took centuries of accumulating evidence to become the uncontroversial starting point it is today. Since then, that same humbling pattern has repeated itself again and again at larger and larger scales. Our star turned out to be one of hundreds of billions in the galaxy. Our galaxy turned out to be one of hundreds of billions in the observable universe. And every single time astronomers have gotten a better instrument and a clearer view, the position Earth occupies has turned out to be less special, not more. Scientists sometimes call this pattern the Copernican principle, after the astronomer who first dislodged Earth from the center of everything. And it's the quiet assumption sitting underneath this entire hour that whatever is true about the conditions on our world and about how quickly and easily life got started here is probably not some cosmic exception. It's probably closer to typical. Every time that assumption has been tested against a bigger telescope, it has held up. This hour is, in effect, asking whether it holds up one more time. At the scale of life itself, that combination ordinary ingredients, on an ordinary world, arriving at life relatively fast, on a planet that has now hosted 4.5 billion years of continuous, unbroken biological history is the entire foundation of the expectation Fermi's question is really built on. If the chemistry that turns into life isn't some once-in-the-universe fluke, if it's instead a fairly natural outcome of common ingredients under common conditions, then it shouldn't have needed a miracle to happen here. And if it didn't need a miracle here, it presumably didn't need one on every other rocky, wet, temperate world scattered across a galaxy that has had 13 billion years to produce them. Run that logic forward. even a civilization only modestly more advanced than ours, with no exotic physics required. Just enough patience and enough time could plausibly spread automated probes or even settlers across the galaxy in a span of millions of years. That sounds long on a human clock. It is a rounding error against 13 billion years if even one civilization at any point in that entire span got a head start of a few 100 million years and kept expanding. The galaxy should already look inhabited, not necessarily colonized by us-shaped beings in visible ships. Just touched, marked, not silent. It's worth being concrete about what touched would actually mean, because the word can slide into vagueness if you let it. It could mean structures. Something like the energy-harvesting megastructures this hour returns to in Chapter 5, built around a star and visible from light years away in the specific wavelengths engineering leaves behind. But nature rarely does. It could mean deliberate or incidental signals, a civilization's own equivalent of radio and television leaking outward, the way Earth's has been leaking outward, faintly, for roughly a century now, or a beacon built specifically to be found. It could mean physical traces closer to home. Probes, relics, or mining activity scattered among asteroids and dead moons. The debris of industry rather than communication. Or it could simply mean a change in a star system's own light output. An atmosphere altered in a way pure geology doesn't produce. A signature written into the physics of a place, rather than broadcast on purpose. None of these requires imagining alien biology, alien psychology, or alien intentions in any detail. They only require imagining that engineering, at a large enough scale, leaves fingerprints, and that 13 billion years is enough time for at least one civilization's fingerprints to have shown up somewhere. This is the rule the rest of this hour is going to test. So let's state it as plainly as possible, without the mysticism that usually gets attached to it. Given the age of the galaxy, the number of candidate stars and planets, and how quickly life appears to get started once conditions allow it, some civilizations should have had enough time to become detectable, and the galaxy has had more than enough time to notice. Notice the wording. This is not a law of physics. It is not a proven fact waiting to be confirmed. It is a probabilistic expectation, built from real numbers and reasonable assumptions, and probabilistic expectations are exactly the kind of thing that can turn out to be wrong for interesting reasons. That's the honest starting position, and it's the one this entire investigation has to be judged against. So the question isn't really, are we alone? That framing is too simple, and it invites too many comfortable non-answers. The real question is narrower and colder. If the expectation is this reasonable, why does the evidence look like the opposite of what the expectation predicts? Before we can answer that, we need to know exactly how carefully that expectation has actually been tested, because we haven't looked, and we've looked hard and found nothing, are two very different problems, and they point toward two very different kinds of explanation. There is one more piece of the expectation worth sitting with before we move forward, because it's the piece most documentaries skip. The expectation isn't just life might exist elsewhere. It's specifically that detectable, expansive life should exist. Civilizations that either broadcast, or build, or travel in ways that leave a trace we could in principle notice from here. A galaxy quietly full of bacteria would satisfy the biological half of the expectation and still look completely silent to our instruments. So the real target of this investigation isn't life. It's the much narrower, much stranger question of technological intelligence, the kind that changes its environment enough to be noticed by a species like us, doing what we are doing right now, pointing instruments at the sky and counting what comes back. One last piece of housekeeping before we go further, because it will save us from a trap this topic falls into constantly. This exact puzzle has generated one of the largest bodies of competing explanations in modern science. In 1983, the scientist and novelist David Brin published a review paper, formally titled The Great Silence, the controversy concerning extraterrestrial intelligent life, that did something nobody had really attempted before. He tried to catalogue essentially every explanation anyone had seriously proposed for the silence, and ended up with something close to 100 distinct candidates. 100. Some overlap, some contradict each other outright, and most of them, on close inspection, turn out to be restatements of a handful of underlying ideas wearing different names. This hour is not going to walk through all 100. That would be exhausting and, frankly, dishonest about which ones actually carry weight. What it is going to do is walk through the small number of explanations that survive contact with the evidence gathered so far. The ones that are still standing after the weakest ones get tested and discarded, one at a time, the way real investigation actually works. If you asked most people how much of the sky has been searched for signs of other civilizations, a common guess is basically all of it. That guess is almost the opposite of true, and getting the actual scale right is the difference between a shrug and a genuine puzzle. The search has a specific starting point, and it's worth knowing exactly where it comes from, because the number attached to it is often repeated without anyone explaining where it came from. In November of 1961, an astronomer named Frank Drake convened a small, informal meeting at the National Radio Astronomy Observatory in Green Bank, West Virginia. He wanted a way to organize the guesswork around one question. How many technological civilizations in our galaxy might currently be capable of communicating across interstellar distances? On a chalkboard, he wrote out 7 terms multiplied together, a formula that starts with the rate of star formation in the galaxy and narrows step by step through the fraction of stars with planets. The number of those planets that could support life, the fraction where life actually starts, the fraction where that life becomes intelligent, the fraction of intelligent species that develop the technology to communicate across space, and finally, the average length of time such a civilization keeps broadcasting before it falls silent, one way or another. That last term carries almost the entire argument on its back, and it's worth pausing on. Every other term in Drake's equation asks about the odds of a civilization arising. Only the last term asks how long it lasts. A galaxy could be a nursery for technological life and still look nearly empty at any given moment. If every civilization that ever appears burns out again within a few centuries, the equation doesn't answer whether that's what's happening. It just makes clear that the answer depends enormously on a term nobody in 1961, or today, actually knows the value of. At the time of that 1961 meeting, only the very first term, the rate of new star formation, had anything close to an observational basis. Astronomers had a rough sense that new stars were forming in the Milky Way at a pace on the order of roughly 1 per year. Every other term in the equation was, honestly, a guess dressed up in the shape of a variable. Drake himself, working from what little the solar system could tell him, estimated that the average star might have somewhere around 2 or 3 planets in a position to support life, a number pulled largely from looking at our own 8 planets and deciding how many of them counted. That's the honest origin of the framework everyone still uses to talk about this question. Not a proof, not a calculation with real inputs, but a shopping list of unknowns, organized cleverly enough that filling in even rough estimates lets you produce a number. And that's exactly the trap. 2 people who disagree about almost nothing scientifically can plug wildly different guesses into those 7 terms and walk away with answers that differ by many orders of magnitude. Anywhere from, we're likely alone in the observable galaxy, to the galaxy should be teeming with thousands of communicating civilizations. The equation doesn't resolve the paradox. It just gives the argument a shape. Some of those terms have gotten dramatically better over the 60-plus years since that chalkboard meeting, though. And this is where the story usually gets rushed past, because the improvement cuts in a direction that makes the silence harder to explain, not easier. The clearest example is the fraction of stars with planets. And more specifically, the fraction with planets sitting in the temperate zone where liquid water could exist on a rocky surface. In 1961, this term was pure speculation, because not a single planet outside our own solar system had ever been confirmed. That changed with space telescopes purpose-built to watch for the tiny, periodic dimming a planet causes as it crosses in front of its star. The result, after years of data, is that potentially habitable rocky planets are not rare exceptions. Estimates of how many Sun-like stars host a roughly Earth-sized planet in their habitable zone vary a lot depending on exactly how researchers define Earth-sized and habitable. Published values in the scientific literature range from a low of a few percent to figures approaching 1 planet per star, which tells you the honest state of the science is still genuinely uncertain, not settled. But even the most conservative end of that published range, applied across the roughly 1 to 400 billion stars in the galaxy, implies a candidate population of potentially habitable worlds numbering, at minimum, in the billions. Billions of candidate cradles is not a fringe estimate. It's close to the low end of the mainstream range, and it means the part of Drake's equation that used to be the biggest unknown has resolved, over 60 years, almost entirely in favor of abundance. Planets like Earth, in the loose sense of rocky, roughly the right size, roughly the right temperature, are not the rare thing anyone in 1961 might reasonably have guessed. They appear to be common. It's worth being precise about what the right temperature actually means here, because the phrase gets thrown around loosely. Astronomers call it the habitable zone. Sometimes, informally, the Goldilocks zone, and the concept is simpler than the name suggests. For any given star, there's a range of orbital distances where a rocky planet with a reasonable atmosphere could sustain liquid water on its surface, neither so close that the water boils away into space the way it did on Venus, nor so far that it freezes solid the way it has on Mars. Every star has its own version of this zone, shifted closer in for dim, cool stars and farther out for hot, bright ones, and the exoplanet surveys behind those billions of candidates estimates are specifically counting rocky worlds that fall inside it. It's a deliberately narrow and conservative definition. It says nothing about atmosphere, magnetic field, plate tectonics, only about the single, checkable variable of orbital distance and surface temperature. Even with that narrow, conservative bar, the count still comes out in the billions. The Drake equation itself, meanwhile, has aged into something closer to a teaching tool than an active research method, and modern researchers studying this question tend to work with more specific, more measurable questions instead. Not, what is the chance of intelligent life, but narrower, checkable versions like, what fraction of Sun-like stars host an Earth-sized planet in the habitable zone, which is precisely the kind of number Chapter 2 just walked through. That's not a failure of Drake's original framework. It's closer to its logical continuation. Instead of one impossibly broad equation with 7 unknowns, the field has splintered into dozens of smaller, answerable questions, each one chipping away, piece by piece, at exactly the uncertainty Drake's chalkboard first tried to organize back in 1961. One distinction is worth holding on to clearly before this chapter moves from ingredients to searching, because it's easy to blur the two together. Habitable and inhabited are not the same claim, and the billions of candidates figure above only supports the first one. A planet sitting in the temperate zone, made of rock, roughly Earth-sized, tells you the physical stage is set. It says nothing about whether chemistry on that particular world ever actually crossed over into biology. let alone whether that biology ever became complex, intelligent, or technological. Every one of the billions of candidate worlds this chapter has been describing is, as far as current instruments can tell, simply a plausible venue. Confirming an audience actually showed up requires an entirely different kind of evidence, which is exactly what the rest of this chapter turns to next. So if the raw ingredients aren't scarce, the obvious next move is to actually go listen. And that brings us to the second half of this chapter. Not what we expect to find, but what we've actually looked for, and how far that search has really reached. The organized effort to detect signals from other civilizations has an actual starting date, and it belongs to the same person who, a year later, would write out the equation this chapter opened with. In April of 1960, Frank Drake pointed the 85-foot radio telescope at Green Bank toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani, each roughly 11 light-years away, and spent several months listening on the specific frequency naturally emitted by hydrogen atoms throughout the universe, reasoning that any civilization doing radio astronomy would eventually notice that same frequency and might use it as an obvious physics-based common channel. He called the effort Project Ozma, after the queen of a fictional, hard-to-reach land in a children's book, and it produced exactly one false alarm, later traced to aircraft radar and otherwise months of ordinary static. It was a tiny effort by today's standards. 2 stars, 1 frequency, a matter of months, but it set the template every search since has followed. Pick a plausible frequency, pick plausible targets, and listen. The most ambitious version of that same basic idea running today is the Breakthrough Listen initiative, launched with the explicit long-term goal of surveying roughly 1 million of the nearest stars for artificial radio and optical signals, an enormous number by the standards of any previous search, and still a number worth putting in context. One published survey from that program, focused on nearby stars using the Green Bank telescope, examined 1,327 target stars across a radio frequency range roughly between 1.1 and 3.45 gigahertz. An earlier related survey covered 692 stars across a narrower slice of that range. These are not small undertakings. Each one represents years of telescope time, enormous volumes of recorded data, and careful analysis designed to flag anything that looks artificial rather than natural. It's worth noting, too, that the search hasn't only run in one direction. Listening isn't the only thing humanity has tried. In November of 1974, the same Frank Drake who wrote the equation this chapter opened with, working with Carl Sagan and colleagues at the Arecibo Observatory in Puerto Rico, used the facility's own megawatt transmitter to deliberately broadcast a message outward, a compact string of just over 1,600 binary digits encoding basic information about arithmetic, human biology, DNA, the solar system, and the telescope that sent it, aimed at a dense cluster of stars roughly 25,000 light-years away. It was less a genuine attempt at conversation than a demonstration and a symbolic gesture, and everyone involved understood that any reply, if one ever came, would arrive tens of thousands of years from now at the earliest, but it illustrates the same asymmetry from the opposite direction. Humanity has been listening for less than a century, and broadcasting, deliberately, essentially once. If the silence partly reflects how little we've announced ourselves, that cuts both ways. It's also a reminder of how little any other civilization, quietly going about its own version of this same search, would have had to work with if it had been listening for us. But hold those numbers up against the scale from Chapter 1. A few thousand stars, out of a galaxy that may contain up to 400 billion. Even the stated long-term goal of 1 million stars is a small fraction of 1% of the galaxy's total stellar population. And every one of those searches is also limited in another way. They only catch a signal if it happens to be broadcast in the specific frequency range being monitored, aimed in a direction that reaches Earth during the narrow window of time the telescope happens to be listening, using a signal strong enough and sustained enough to stand out from natural radio noise. Widen any one of those constraints. A civilization broadcasting on a different frequency, or only briefly, or not toward us at all, or using a communication method that doesn't look anything like a radio signal, and it slips through a search that otherwise looks thorough. This is the piece that gets lost when people casually say, "We've looked and found nothing, so there's probably nothing there." What we've actually done is examine an extremely specific, extremely narrow slice of a much larger possibility space. A handful of thousands of stars in certain frequency bands for finite windows of time, and found nothing artificial in that slice. That is a real result. It is not nothing, but it is also nowhere near the exhaustive search the phrase, "we've looked everywhere," implies. There is exactly one moment in this entire search's history worth pausing on, because it's the closest anyone has ever come to a genuine hit, and its fate tells you something important about how unforgiving this kind of evidence actually is. On the 15th of August, 1977, a fixed radio telescope in Ohio called Big Ear, built to sweep the sky using nothing more than the Earth's own rotation, picked up a burst of narrowband radio noise lasting 72 seconds, arriving almost exactly at the frequency associated with neutral hydrogen, a frequency many SETI researchers had long argued would be a logical one for another civilization to use, since it's a physical constant any technological species doing radio astronomy would eventually notice. The volunteer astronomer reviewing the printout circled the reading and wrote a single word in the margin: "Wow." Nearly 50 years of follow-up observations, using instruments far more sensitive than Big Ear ever was, have never found it again. No repeat, no source identified with confidence, no confirmed mundane explanation despite genuine attempts. Comet activity and satellite reflections have both been proposed, and neither has closed the case. It remains, to this day, unexplained. Not evidence of contact, not proof of anything, just a single 72-second anomaly that illustrates exactly how thin the line is between the most tantalizing signal ever recorded and gone before anyone could look twice. And a reminder that even our best-known near-miss still isn't the exception the numbers from Chapter 1 are asking for. Radio silence, though, is only half of what looking means today. And the other half has changed dramatically in just the last few years, in a way worth naming before this chapter closes. Alongside listening for deliberate signals, a newer and arguably more direct approach has become possible. Reading a planet's atmosphere itself for chemical evidence of biology, whether or not anyone out there is trying to communicate at all. The James Webb Space Telescope, since becoming operational, has given researchers their first genuine opportunity to attempt exactly this, analyzing the faint starlight that filters through an exoplanet's atmosphere as it passes in front of its star, looking for the chemical fingerprints, called biosignature gases, that living systems tend to produce, and that are hard to explain any other way. It's a fundamentally different kind of search than anything in this chapter so far. Not listening for someone else's technology, but reading a planet's own chemistry for the passive signature of life simply existing. The honest caveat, straight from the researchers doing this work, is that it's still extraordinarily difficult. An Earth-sized planet around a sun-like star produces a signal far too faint for even Webb to reliably read. And even the more favourable case of an Earth-sized planet around a smaller, dimmer star remains a serious technical challenge. More capable instruments, including a new generation of ground-based telescopes expected later this decade, will be needed before this method can deliver a confident result either way. But the method itself, unlike a radio search, doesn't require anyone to be trying to talk to us. It only requires life to exist, doing what life does to the air around it, which makes it, in principle, the most patient and least anthropocentric search humanity has ever attempted. So here is where that leaves the argument honestly stated on both sides. The ingredients for life, habitable worlds, appear to be common, likely numbering in the billions across the galaxy, which strengthens rather than weakens the original expectation from Chapter 1. At the same time, the search for signals of technological civilization has covered only a tiny, specific fraction of the galaxy's stars, under a narrow set of assumptions about how those civilizations would choose to announce themselves, which means the total silence we've measured so far is a real, meaningful, but still incomplete data point, not a verdict. Lay the whole history of this search side by side, and a pattern emerges that's easy to miss when each piece is considered on its own. 65 years separate Frank Drake's 2 nervous months listening to 2 nearby stars in 1960 from the multi-decade million-star ambitions of breakthrough listen today, with an unexplained 72-second anomaly and one deliberate, symbolic outbound message sitting in between, and an entirely new method, reading a planet's atmosphere directly for the chemistry of life, only now becoming possible for the first time in human history. Each generation of this search has been larger, more sensitive, and more methodologically varied than the one before it. None of them, across 65 years, has produced a confirmed detection. That's not evidence the search has been badly designed. If anything, the steady widening of methods, from 1 frequency and 2 stars, to millions of stars across a wide radio band, to the chemical fingerprints in starlight itself, is what a genuinely serious, evolving scientific effort looks like. It's exactly the kind of expanding, increasingly rigorous search that makes the continued silence harder to wave away with each new decade, not easier. That distinction is the hinge this entire hour turns on. If the search were genuinely exhaustive and still came back empty, that alone would be one of the strangest results in the history of science. It isn't exhaustive, and yet, as the next chapter is going to show, even accounting honestly for how limited our search actually is, there is a separate argument, one that has nothing to do with radio telescopes at all, that suggests the silence should still be much less complete than it currently is. That argument is where the comfortable explanations start to run out of road. There are 4 explanations most people reach for instinctively when they hear about the silence, and all 4 feel reasonable. We haven't searched long enough. Life is probably just rare. Space is too big to cross anyway. So, absence of contact doesn't mean absence of life. And the one that tends to come up last, usually as a kind of trump card, maybe they're already here, watching, and simply choosing not to announce themselves. Each one sounds like it should end the conversation. None of them actually does, and it's worth watching exactly where each one fails, because the failures compound. Start with, we haven't searched long enough, since Chapter 2 already did most of the work here. It's true that our radio search has covered only a sliver of the galaxy's stars, but notice what that explanation actually concedes. It doesn't claim the galaxy is empty. It claims we simply haven't caught anyone yet. The way you might not spot a single specific person in a city of 10 million by glancing down one street. That's a coherent excuse for our silence. It is not an excuse for theirs. A truly ancient, truly expansive civilization wouldn't need us to find its radio signal because it wouldn't need to be found. It would already be spreading, physically, leaving traces that don't depend on anyone aiming a dish at the right star at the right moment, which means we haven't searched enough only explains why we might miss a quiet, cautious civilization. It does nothing to explain why we don't see an expansive one. And an expansive one is exactly what the numbers from Chapter 1 predict should exist. If even a single technological species anywhere in 13 billion years got a sufficient head start, that leads straight into the second excuse. The one that sounds the most physical and the most reassuring. Space is simply too big. Interstellar distances are staggering, the argument goes, so even if other civilizations exist, they're probably too far away, or travel is too slow for anyone to ever actually reach us. This is where the math stops cooperating with the comfortable version of the story. You do not need faster than light travel, wormholes, or any exotic, undiscovered physics to make this argument fail. You only need patience, and 13 billion years is an almost absurd amount of patience to work with. And a small fraction of the speed of light isn't purely theoretical either. It's roughly the regime humanity itself has already started sketching out engineering for. A privately funded research initiative called Breakthrough Starshot has laid out a concept, still unproven at full scale but grounded in existing laser and materials physics, for accelerating gram-scale probes to around 20% of light speed using a ground-based array of lasers pushing against an ultra-thin sail. Fast enough, on paper, to reach the nearest star system beyond our own in roughly 2 decades rather than the tens of thousands of years today's fastest spacecraft would require. Whether or not that particular project ever flies, it illustrates the point plainly. A species barely a century into powered flight can already draw up serious, physics-respecting blueprints for crossing interstellar distances in a single human lifetime. A civilization with even a few thousand additional years of head start would not need anything humanity doesn't already, in outline, know how to attempt. And it wouldn't need crude ships making the whole journey in one go either. Automated probes, built to construct copies of themselves at each new star system the way a single seed can eventually produce a forest, could plausibly cross the entire 100,000 light-year width of the Milky Way, crawling at that same modest fraction of light speed in a span on the order of tens of millions of years. That sounds enormous on a human scale. It is a rounding error against the age of the galaxy. 10 million years is roughly 1 part in 1300 of 13 billion years. If you compress the galaxy's entire history into a single 24-hour day, a 10 million year colonization wave takes about 1 minute to sweep from one side to the other. Picture it a different way. Because the abstraction of 13 billion years is hard to feel in your body, and feeling it is the entire point of this section. Imagine every star in the galaxy lighting up, one at a time, in the order it formed, across a single human lifetime compressed to 80 years. On that timeline, the Milky Way itself would have been forming stars from around the moment that lifetime began. Our own sun wouldn't ignite until deep into that person's 50s. Earth would form and cool a little after that. The very first life on Earth would appear within about a year of the planet's formation on this compressed clock, matching the actual, real pace this hour has already established. And the entire span of recorded human civilization, every pyramid and empire and war and rocket launch, would occupy less than the final second of that 80-year life. Against a timeline like that, a colonization wave lasting a mere 10 million real years wouldn't even register as a heartbeat. It's not that interstellar travel is trivial, it's that the amount of time available for even one lucky success to occur is so enormous that we just haven't had time yet. Stop sounding like an explanation and start sounding like a category error. This is the argument that turned Fermi's lunchtime question into an actual paradox rather than just idle wondering, and it was formalized by the astronomer Michael Hart in 1975 and extended by the physicist and cosmologist Frank Tipler shortly after. Their point wasn't that interstellar travel is easy, it's that it doesn't need to be easy. It only needs to be possible at all, using engineering not wildly beyond extrapolations of what we can already imagine. And it only needs to happen once, anywhere, at any point across billions of years for the galaxy to end up thoroughly filled. Space is too big is a reasonable objection to one civilization visiting one other star within one human lifetime. It stops being a reasonable objection once you're allowed 13 billion years and any one of hundreds of billions of candidate starting points. So distance, on its own, isn't the wall people assume it is. That leaves the third excuse, the one that actually deserves the most respect. Because unlike the first two, it isn't obviously wrong. It's just deeply uncertain. Maybe the ingredients are common, and maybe the travel time problem is solvable in principle. But maybe the step that's actually rare is life itself, or at least the complex, multicellular version of it. This is the position formally argued in the year 2000 by the paleontologist Peter Ward and the astronomer Donald Brownlee in a book that named the idea the rare Earth hypothesis. Their case wasn't that simple. Microbial-level life is scarce. They were comfortable granting that it might be common, but that the further combination of factors needed to support complex, large-scale organisms, things like a stable orbit, a large stabilizing moon, plate tectonics, and a long, undisturbed stretch of geological history, is a much taller order, one that might be satisfied on vanishingly few worlds, even in a galaxy otherwise full of simple biology. It deserves to be taken seriously rather than waved away, not treated as a fringe position. It's a mainstream published scientific argument. Just one this hour is about to stress test the same way it has tested everything else. Here's where it gets genuinely uncomfortable though, and it connects directly back to the numbers from Chapter 2. Even the published estimates for how many stars host a roughly Earth-sized planet in the temperate zone span a wide range. Depending on definitions and methods, researchers have published figures from a low of a few % of stars up to nearly one habitable zone rocky planet per star. That is a wide, honestly uncertain range, and it should be treated as one. But run the arithmetic even at the pessimistic end of that range, against a galaxy of at minimum 100 billion stars, and you still land on a candidate population of habitable worlds in the billions. Billions of candidate worlds, each one a separate roll of the dice for the chemistry that leads to life. The rare Earth argument doesn't need life to be common. It just needs it to not be so staggeringly rare that not one success occurs among billions of independent attempts, spread across billions of years. That's a very specific, very extreme kind of rarity to require, and it's the minimum rarity the excuse actually needs in order to work. None of this proves life is common. It's entirely possible that the step from chemistry to biology genuinely is that rare. Rare enough to beat odds of 1 in billions and still land on zero elsewhere. Science doesn't currently have the data to rule that out, but notice what's happened to the argument. We haven't looked enough, explains our ignorance, not their absence. Space is too big, collapses once you take the actual timescales seriously, and life is probably rare, survives only by demanding an extraordinarily specific, currently unverifiable kind of rarity. Not impossible, but no longer the comfortable default explanation it's usually treated as. That leaves the fourth explanation, the one that usually gets raised half-jokingly, but deserves to be taken exactly as seriously as the other three, because someone did take it seriously, formally, decades ago. In 1973, the same year John Ball coined the term, the Harvard astrophysicist proposed what's become known as the zoo hypothesis, the idea that one or more advanced civilizations already know we're here, are entirely capable of contacting us, and have made a deliberate choice not to, treating our solar system, in effect, as a protected reserve, observed but not disturbed, the way a wildlife sanctuary has managed to interfere with its inhabitants as little as possible. It's an elegant idea, in a way, because it doesn't require anyone to be absent. It just requires them to be quiet, on purpose, out of restraint rather than inability. Here's where the zoo hypothesis runs into the same wall every other comfortable explanation in this chapter has run into, though just from a different direction. It can account for our silence toward them, sure. If they're deliberately hiding, of course we haven't found them, but it demands something much stranger to hold up as an explanation for the entire galaxy's silence. Not just our own particular case, universal agreement. Not one civilization choosing restraint, But every single technological civilization that has ever existed across billions of years and billions of candidate worlds, independently arriving at and perfectly enforcing the exact same policy of total non-interference, with zero defectors, zero accidents, zero curious outliers, and zero enforcement failures for the entire multi-billion-year span this hour has been working with, coordinating that kind of unanimous, unbroken silence across a galaxy's worth of independently evolved civilizations, most of which would never have had any contact with each other at all, is arguably a harder problem to explain than the silence itself. It doesn't remove the tension, it just relocates it from why is nobody visible to why would literally everybody, with no exceptions ever, agree to the same restraint. And that second question is, if anything, less comfortable than the first. Take all four away, and you're left standing in the same place. Fermi's reconstructed question left you 70 years ago, except now it's sharper because it's no longer resting on a vague sense that the universe is big and space is empty. It's resting on a chain of specific, checkable reasoning. The ingredients appear common, the timescales are more than sufficient, and the search that's come up empty is real but partial. The comfortable exits are closed, one at a time, not by speculation, but by the same kind of ordinary, checkable numbers that got us into this question in the first place, which means the silence needs an actual mechanism now, not an excuse, not a shrug, but something that would specifically and reliably keep civilizations from becoming loud, expansive, and visible across every single opportunity the galaxy has had to produce one. That's a much stronger requirement than most explanations offer. And there's exactly one framework built to meet that requirement head-on. In August of 1996, an economist named Robin Hanson, not an astronomer, not a physicist, an economist by training, which turns out to matter for how clearly he was able to see the shape of the problem, published an essay that gave this whole puzzle its sharpest name yet. It's worth pausing on why that particular professional background mattered here. Economists spend their careers thinking about scarcity, competition, and the uneven distribution of rare successes. Why only a handful of companies out of thousands of attempts ever become dominant. Why most new ventures fail quickly while a tiny few compound into something enormous. That's a different set of instincts than an astronomer or physicist typically brings to a question like this. And it's arguably exactly the right toolkit for noticing that the galaxy is silent isn't fundamentally a question about telescopes or rocket engines at all. It's a question about where, along a long chain of high-stakes, winner-take-almost-nothing attempts, the real bottleneck to success is actually sitting. The same kind of question an economist asks about markets, just aimed outward at the history of life itself. He called it the Great Filter, and the core of the idea is almost brutally simple once you hear it stated plainly. Somewhere between dead matter and a civilization visibly expanding across its galaxy, there exists at least one step that is so difficult, so improbable, that it filters out nearly everyone who attempts the journey. Life gets started constantly, across billions of worlds. Almost none of it makes it all the way through. Something, at some stage along that path, is doing the filtering. Hanson's essay reduces the entire argument to a single uncomfortable sentence. Nobody makes it. Not nobody has made it yet. Not we haven't found the ones who did. Nobody, out of an enormous number of attempts, has become the kind of loud, galaxy-spanning civilization that 13 billion years and billions of candidate worlds should statistically have produced by now. Something is stopping almost everyone, almost every time. Part of why that essay has stayed so influential for 3 decades, cited across astronomy, philosophy, and existential risk research alike, is that it does something most explanations for the silence don't even attempt. It doesn't just describe the silence. It makes a falsifiable in-principle claim about the structure hiding underneath it. A vague statement like, life is mysterious or the universe is big, can't really be tested or refined. There exists a specific, identifiable bottleneck step, and its position relative to us determines our own odds, is a claim that can, in principle, be narrowed down as evidence accumulates, which is exactly what the rest of this hour has been doing, chapter by chapter, treating each new piece of evidence as one more data point for locating where on that list the bottleneck actually sits. Here's what makes the Great Filter more useful than the vague word rare that people usually reach for. It doesn't just say the outcome is unlikely, it insists that unlikeliness has to live somewhere specific, at some identifiable stage in the chain of events between simple chemistry and a technological civilization spreading among the stars. And once you frame it that way, you can actually list the candidate stages in rough order and ask a pointed question about each one. Is this the hard step, or have we already gotten past it? The list looks something like this, moving from earliest to latest, and it's worth slowing down on each one, because the entire rest of this hour depends on knowing exactly what's being asked at every stage. Step 1. The formation of the right kind of star and planet, with the right chemistry available in the right place. Rocky, not gaseous. Warm enough for liquid water. Not so warm it boils away or so cold it stays locked as ice. As Chapter 2 already established, this step appears to be common, likely producing billions of candidates across the galaxy alone. The actual transition from complex, non-living molecules to something that counts as alive, capable of copying itself and passing on small variations. This step remains genuinely mysterious, even for the one example we have any data on at all, our own. Scientists have proposed multiple plausible chemical pathways, but none has been confirmed as the one that actually happened here, let alone shown to be common or rare across other worlds. Step 3. The jump from simple, bacteria-like life to complex cells with internal structure. The merger this hour will return to in detail in Chapter 7. On Earth, that transition took an extraordinarily long time relative to how quickly simple life first appeared, which some researchers take as a hint that it might be a rare, difficult step rather than an easy, inevitable one. Step 4. The jump from single, complex cells to multicellular organisms working together as one coordinated body. Plants, animals, fungi, all the visible, macroscopic life most people picture when they hear the word life at all. Step 5. The evolution of something recognizable as intelligence, in the sense of flexible problem-solving, learning, and eventually abstract reasoning and tool use, rather than fixed, purely instinctive behavior. Step 6. The development of technology sophisticated enough to be detectable across interstellar distances. Not just tool use, but industrial-scale, energy-intensive civilization capable of leaving a mark visible from other star systems. And Step 7, the one almost no casual conversation about this topic ever mentions, and the one that turns out to matter most for everything the rest of this hour builds on. The survival of that technological stage for long enough, and its expansion far enough to actually become visible on a galactic scale, rather than flickering out shortly after it begins, the way a candle can light and gutter out within the same breath. 2 of those 7 steps are going to matter more than the others for the rest of this hour, and it's worth flagging them now so the argument doesn't feel like it's pulling a new idea out of nowhere later. Step 3. The jump from simple to complex cells is the leading candidate many researchers point to for a filter sitting safely behind us, precisely because of how rare it looks in Earth's own fossil record, and this hour returns to it in detail in Chapter 7. Step 7. Survival and expansion, after reaching roughly our own current stage, is the leading candidate for a filter still ahead of us, because it's the one step this hour's evidence about self-destruction risk speaks to most directly. And it's the subject of Chapter 6. Everything Hansen's essay actually establishes is more modest than picking a winner between those 2. It's the logical demonstration that the winner has to be one specific step or another, not a diffuse fog of general unlikeliness spread evenly across the whole list. Now here is the part of Hansen's argument that turns an interesting classification exercise into something genuinely unsettling. So listen closely, because this is the idea the rest of the hour builds on. The filter has to sit somewhere on that list, and its position relative to us changes everything about what the silence means for our own future. If the hard step, the true bottleneck, the one responsible for almost everyone failing, sits behind us, in our past, then we've already beaten the odds. We're one of the vanishingly rare success stories, and whatever waits ahead of us on that list is comparatively easy, since so few other candidates ever got far enough to test it. In that version of the story, the silence is almost good news. It means we cleared the hardest part already, simply by existing as a technological species at all. And the road ahead, while not guaranteed, is not statistically loaded against us in some hidden way. But if the hard step sits ahead of us, somewhere between where we are right now and the kind of galaxy-spanning visibility this entire hour has been building the case for, then the math runs the other direction. And it runs hard. It would mean that every civilization that ever reaches roughly our stage of development, using roughly our kind of technology, at roughly our level of expansion into space, goes on to fail the very next test. Not most of them, nearly all of them. Every single one of the countless candidate worlds from Chapter 1, every one of the billions of habitable planets from Chapter 2 that got exactly this far, and then didn't get any further. That's not a coin flip. Given the numbers already on the table, a filter ahead of us would have to be close to absolute, eliminating something like nearly all civilizations that reach our current stage, to be consistent with a galaxy that still looks this empty. This is Hansen's actual conclusion, and it's worth stating in his own logic, rather than softening it. The easier it looks for life to reach our current stage of development, the worse the news is if we still haven't seen anyone past it. Every discovery that makes the earlier steps look more common, every new habitable planet, every hint that life starts easily, every piece of evidence chipping away at the "we're a lucky fluke" explanation, quietly shifts the weight of the whole argument toward the version where the dangerous step is still ahead of us, not behind. And notice what chapters 1 through 3 already did to that balance. Without anyone stating it this bluntly at the time, they made the early steps look more common, not less. Habitable worlds, common, likely in the billions. Life starting quickly once conditions allow, at least plausible, based on Earth's own early biological record. Travel across galactic timescales, not actually the barrier it's usually assumed to be. Every one of those findings, taken individually, sounded like good news. Evidence that the universe is fertile, that we're not some impossible cosmic accident. Taken together, inside Hansen's framework, they do something closer to the opposite. They push the likely location of the Great Filter later in the sequence, closer to us, possibly still in front of us. That's the reclassification this entire investigation has been building toward. And it changes the emotional shape of everything that came before it. The silence stops being a mystery to solve for its own sake, the way it might feel in Chapter 1, and becomes something closer to a diagnostic test already in progress. One where the results, so far, are not neutral. They're leaning in a specific and specifically unsettling direction. To be clear about what this argument does and doesn't establish, because precision matters more here than anywhere else in this hour. Hansen's Great Filter is a logical framework, not a discovered fact. It doesn't tell us which step is the hard one. It doesn't prove the filter is ahead of us rather than behind. What it does is force a choice that most casual conversations about aliens manage to avoid entirely. Either the hard step already happened to us, or it's still coming. There is no comfortable third option where the filter simply doesn't exist. Not once you've accepted the numbers from the first 3 chapters. Something, somewhere along that list, is filtering out nearly everyone. The only real question left is when. It's worth adding, before moving on, that Hansen's essay wasn't the end of this line of research, just the beginning of it. In the years since, other researchers have tried to move the Great Filter from a compelling piece of reasoning towards something closer to a formal, testable statistical model, taking everything currently known about star formation rates, planet occurrence, and the pace of biological evolution on Earth, and asking what range of filter positions that data actually allows, rather than simply arguing about it qualitatively the way this hour has been doing so far. That work is ongoing, genuinely technical, and still produces a wide range of possible answers depending on which assumptions go in, which is itself an honest reflection of how much remains unknown. But the direction of travel in that research community is worth noting plainly. It has tended to reinforce Hansen's original warning rather than undercut it, because every additional piece of hard data about how common the early steps are narrows the space in which a filter safely behind us remains the more probable reading. A fair objection to everything so far is that this whole argument has been built almost entirely around radio signals, narrow slivers of frequency aimed at a few thousand nearby stars over a search that's barely begun by galactic standards. Maybe that's simply the wrong place to look. So this chapter widens the lens, on purpose, to two very different kinds of evidence. The actual math behind how fast a civilization could physically spread, worked out in detail rather than approximated, and a completely different category of search. Not for signals, but for structures. Start with the math, because Chapter 3's version of it was deliberately conservative, and the real numbers, when researchers have actually sat down and calculated them, are more extreme than tens of millions of years. In his original 1975 paper, Michael Hart worked through a specific scenario. Starships traveling at roughly 1/10 the speed of light, spending time at each new star system before launching the next wave outward. His result was that a colonization wave under those assumptions could sweep across the entire galaxy in about 650,000 years. And even being generous about the time needed for each new colony to establish itself before continuing outward, the total came to around 2 million years. 2 million years against a galaxy that has existed for roughly 13 billion. That's not a close call. That's the colonization wave finishing, while the rest of the galaxy's history still had more than 6,000 times as long left to run. Frank Tipler pushed the argument further in 1980, working with a different mechanism entirely. Not crewed starships, but self-replicating probes. Machines that arrive at a new star system use local material to construct copies of themselves and send those copies onward to the next system, the way a single seed can eventually produce a forest. The underlying concept wasn't Tipler's own invention. It traces back to the mathematician John von Neumann, who worked out the formal logic of machines capable of building working copies of themselves from raw material back in the 1940s, well before space travel of any kind was practical, purely as a question in mathematics and automata theory. Tipler's contribution was to point that same idea outward, at the galaxy, and ask what happens if you let a von Neumann-style self-replicating machine loose among the stars instead of confining it to a laboratory thought experiment. Tipler's calculation, using nothing more exotic than an extrapolation of spacecraft speeds already achievable at the time he was writing, put the galaxy-spanning timescale at under 300 million years. Slower than Hart's estimate, because self-replicating probes weren't assumed to move anywhere near 1/10 of light speed, but still almost unimaginably fast against a 13 billion year backdrop. 300 million years is roughly the span separating the earliest dinosaurs from today. On the scale this hour has been building since Chapter 1, it is close enough to instantaneous that it barely registers. It's worth being fair to the pushback here too, because the honest version of this argument includes its critics, not just its advocates. In 1981, two other researchers, Newman and Sagan, argued that Hart and Tipler's numbers rest on an assumption that doesn't obviously hold, that a colonizing civilization keeps expanding its population at a high, sustained rate at every new world it settles. Model the expansion instead with more modest, demographically realistic growth rates. They showed, and the time needed to fill the galaxy can stretch out dramatically, potentially approaching or even exceeding the galaxy's own age. Their point wasn't that interstellar travel is impossible. It was that fast ships and fast colonization aren't automatically the same claim. A civilization could have the technology to cross interstellar distances and still choose, or be forced by circumstance, to expand slowly enough that a still empty-looking galaxy remains genuinely possible without needing any filter at all. That's a real, serious objection, and it deserves to sit in this hour honestly rather than get steamrolled for the sake of a tidier story. But notice what it actually concedes and what it doesn't. It concedes that colonization speed depends on choices and constraints, not just raw engineering capability. It does not remove the requirement from Chapter 1 that this pattern would only need to happen once, successfully, anywhere, across the entire multi-billion-year history of the galaxy to eventually become visible. Nor does it explain why every single civilization, across billions of candidate starting points, would happen to choose or be constrained toward the slow, quiet path, with not one single exception detectable anywhere. A slower expansion rate weakens the strongest version of the Hart-Tipler argument. It doesn't remove the underlying tension. It just means the silence, if there is a benign explanation, might be a story about universally cautious or universally resource-constrained expansion, which is itself a strange thing to be true of literally everyone, everywhere, with zero exceptions ever detected. More recent research has tried to model this middle ground more carefully. Civilizations that do expand, but not as an unstoppable wave sweeping the whole galaxy in one uniform pass. These steady-state models allow for settlement that stalls, restarts, spreads unevenly, and leaves gaps. The way human colonization of a landmass historically has, rather than the perfectly uniform expansion the simplest Hart-Tipler math implicitly assumes. Under some versions of this kind of model, a galaxy could contain expanding civilizations for its entire history and still have large regions, including possibly our own neighborhood, that simply haven't been reached yet, purely as a matter of geography and timing rather than any filter at all. This is a genuinely useful refinement, and it deserves to be taken seriously as one of the more sophisticated, benign explanations on the table. But it comes with the same structural problem every benign explanation in this hour eventually runs into. It has to apply to everyone, everywhere, with no exceptions, for the entire history of the galaxy in order to fully explain a total absence rather than a partial one. A model where colonization is patchy and uneven predicts a galaxy with some regions settled and others not. Not a galaxy where the region we can actually observe closely, our own stellar neighborhood, contains no confirmed trace of anyone at all, past or present, expanding or otherwise. Which brings this chapter to its second kind of evidence. Because if slow, deliberate colonization were the real answer, there's a specific signature it should still leave behind, one that has nothing to do with radio broadcasts at all. A civilization advanced enough to expand meaningfully across even a single star system, let alone many, would need enormous amounts of energy. And the most efficient way to collect a star's entire energy output, at least in principle, is to surround it with structures engineered to capture that light. In 1960, the physicist Freeman Dyson, a researcher who spent his career comfortable working at the boundary between rigorous physics and genuinely speculative engineering, published a short paper making exactly this argument in the journal Science. His reasoning was almost ruthlessly practical. Any civilization that keeps growing its energy use for long enough, he argued, will eventually run out of room on the surface of its home planet and be forced to expand its energy-collecting infrastructure outward into space around its own star. Push that logic far enough into the future, and the natural endpoint isn't a bigger version of a solar panel field. It's some kind of structure or swarm of structures encircling the star itself, capturing a meaningful fraction of its total energy output rather than the tiny sliver a single planet receives. Dyson wasn't claiming anyone had actually built one. He was pointing out that if a civilization kept growing long enough without hitting some other limit first, this is roughly what the endpoint should look like from the outside, and, crucially, that it would be detectable using ordinary physics. No special assumptions about alien psychology required. The idea became known as a Dyson sphere, and it comes with a very specific, very findable signature. A star's visible light gets captured and used, but the waste heat from that use has to go somewhere, and physics says it radiates back out as infrared. A star behaving exactly like a normal star in visible light, but radiating strangely, characteristically in infrared, the way an engineered structure, rather than a natural object would, is precisely the kind of anomaly a telescope could catch, without needing anyone to broadcast anything on purpose. Researchers have actually gone looking for exactly this, using data from the Wide Field Infrared Survey Explorer, an orbiting telescope that mapped the entire sky in infrared light. A research program sometimes referred to by the acronym GHAT, short for Glimpsing Heat from Alien Technologies, systematically searched large numbers of galaxies for the specific infrared signature, a civilization capturing a huge share of its galaxy's stellar energy output would produce. The result? Stated plainly in the published research. That kind of galaxy-spanning energy use appears to be rare or effectively absent in the local universe. Not one clear, confirmed candidate. Later, more targeted searches have applied similar reasoning on smaller scales, looking for partial Dyson structures around individual stars using combined data from multiple sky surveys. Again, turning up candidates worth further study, but nothing confirmed as artificial. It's worth being honest about how hard this particular kind of search actually is, because unusual infrared glow is not, by itself, proof of anything artificial. Ordinary astrophysics produces plenty of infrared excess on its own. A disk of natural dust orbiting a young star, for instance, radiates in a way that can superficially resemble the signature a Dyson structure would leave, which means every genuinely promising candidate this kind of survey turns up has to be checked carefully against a growing list of mundane explanations before it can be taken seriously as unusual. Every search described in this chapter, in other words, has to work hard to rule out ordinary nature before it can even begin to ask about engineering, which cuts in an important direction for how much weight the null result should actually carry. A search that struggles to reliably tell artificial from natural is not a search whose nothing found result should be treated as a clean, confident absence. It should be treated exactly like the radio search from Chapter 2. A real, meaningful, but still partial and imperfect result, not a verdict. Put the two halves of this chapter next to each other, and the picture sharpens rather than softens. The purely mathematical argument says that even a slow, resource-constrained, demographically cautious expansion should, across billions of years and billions of candidate civilizations, have produced at least some visible outliers. Some faster expanders, some less cautious ones, some who simply got lucky with an easier path. And the structural search says that even setting aside radio signals entirely and looking instead for the physical footprint of large-scale energy use, the galaxies we've been able to examine show no confirmed sign of it either. Two independent lines of evidence, built on completely different physics, one about population dynamics and travel time, one about infrared radiation and energy capture, and neither one turns up the thing the numbers from Chapter 1 said should exist somewhere. By now, at least once. This is the point where maybe we just haven't looked in the right way yet, starts to strain under its own weight. We've looked with radio telescopes tuned to specific frequencies. We've looked with infrared telescopes tuned to the waste heat of large-scale engineering. We've run the travel time math generously and run it conservatively. And even the conservative, criticized version doesn't erase the tension. It just softens one edge of it. Every additional method of looking narrows the space where a comfortable, filter-free explanation can still hide. None of this, it's worth repeating clearly, proves the Great Filter is real, or proves where it sits. What it does is close off another set of exits. It's not simply that we haven't caught a signal, it's that we haven't caught a structure, a heat signature, or a population growth pattern inconsistent with total absence. Across every independent way scientists have devised to test for one, the silence isn't just holding in one channel, it's holding across all of them, which leaves one honest, uncomfortable question standing at the center of everything gathered so far. If the ingredients are common, if the timescales are sufficient even under conservative assumptions, and if every independent search for a footprint keeps coming back empty, what, specifically, is doing the filtering? Not, is there a filter? That question, after 4 chapters, is close to settled. The question now is which candidate mechanism actually fits. And that means finally naming the possibilities. Most conversations about this topic are too uncomfortable to sit with for long. There are 2 very different kinds of dark explanation that tend to get lumped together whenever this topic comes up. And separating them cleanly is the most important thing this chapter does. One of them is a sober, published, peer-reviewed line of academic risk analysis. The other is a vivid idea from a science fiction novel that has, understandably, leaked into popular conversation as though it carries the same evidential weight. It doesn't, and pretending otherwise would break the promise this entire investigation has been keeping since. Chapter 1. Use fatos verificáveis. Don't manufacture certainty the evidence doesn't support. So let's take them one at a time, in the right order, starting with the one that has actual scholarship behind it. The academic version of this candidate filter is usually discussed under the heading of existential risk, a term formally defined by the philosopher Nick Bostrom in a 2002 paper as any risk where the outcome would either annihilate Earth-originating intelligent life outright or permanently and drastically cut off its future potential. Bostrom's point, made explicit at the start of that field of research, was that humanity had entered a period where its own accelerating technology, not just natural catastrophe, but the tools of our own making, had become a plausible source of exactly that kind of ending. Nuclear weapons were the first clear example. Since then, researchers in this field have added others to the list. Engineered pandemics, potentially far more lethal and far more controllable than anything that evolved naturally. The possibility of advanced artificial intelligence systems pursuing goals badly misaligned with human survival. And slower burning risks like catastrophic, irreversible damage to the systems that keep a planet habitable in the first place. The philosopher Toby Ord took this analysis further in a widely discussed 2020 book, attempting to put actual numbers on the risk facing humanity specifically over the coming century. His estimate, and it's important to be precise that this is one researcher's considered judgment, not a measured, agreed-upon scientific constant. The way the age of the universe is put the total chance of an existential catastrophe within the next 100 years, at roughly 1 in 6. Broken down further, Ord estimated that risk is overwhelmingly dominated not by the threats most people instinctively fear most, but by newer ones. He placed the risk from unaligned artificial intelligence at around 1 in 10 over the century, higher than every other category combined, while placing the risk from nuclear war specifically at around 1 in 1,000 over the same period. Bostrom returned to this problem again in 2019 with a paper built around a single, deliberately unsettling image. Imagine human creativity, he suggested, as a giant urn full of balls, and every new technology humanity ever invents as another ball pulled out and set on the table. Most of the balls are white, beneficial, or at worst mildly harmful. Some are various shades of grey. Technologies with real costs alongside real benefits, requiring management but not existential caution. What Bostrom calls the vulnerable world hypothesis is the possibility that somewhere in that urn sits at least one black ball, devastates the civilization that discovered it almost by default, unless that civilization has already built the institutions needed to control it before anyone reaches in and pulls it out. His unsettling observation is that we don't get to inspect a ball before it's drawn. We only find out what color it was after. Nuclear weapons, Bostrom argues, came uncomfortably close to being a black ball and were only kept from truly catastrophic default outcomes by fortunate, and to some extent lucky, institutional decisions made in the decades since. The open question this hour has been circling since Chapter 4 is simple and sobering. How many more draws does a typical civilization get at roughly humanity's current stage of development before pulling one it can't survive? And is that number, on average across the galaxy, closer to many or closer to one? Put a little more texture on the specific categories researchers in this field actually study, because existential risk can otherwise stay too abstract to feel real. Engineered pandemics sit high on most researchers' lists because, unlike naturally evolved diseases, which are shaped by evolutionary pressure to keep spreading rather than to kill efficiently, a deliberately or accidentally engineered pathogen isn't constrained by that same evolutionary logic. And the underlying biotechnology needed to attempt this has become steadily more accessible over time. Advanced artificial intelligence sits even higher on Ord's own list, specifically because of a property most other risks don't share. Once a sufficiently capable system is pursuing goals not properly aligned with human survival, correcting the mistake after the fact may not be possible in the way it would be with, say, a badly regulated industry. You may not get a second attempt, and slower risks, like irreversible damage to the planetary systems a civilization depends on, matter for a different reason. They don't need a single catastrophic event at all, just a species collectively unable to coordinate fast enough to stop a slow-moving problem before it becomes an unsolvable one. 3 very different mechanisms, one shared structural feature. Each becomes available to a civilization only after it crosses roughly the same rough threshold of technological capability. The threshold humanity is living inside of right now. There's a structural reason this particular category of risk clusters so tightly around one narrow window in a civilization's history, rather than being spread evenly across its entire lifespan, and it's worth making explicit rather than leaving implied. Biological evolution, the process that built human brains, human instincts, and human institutions in the first place, works on timescales of tens of thousands to millions of years. Technological change, by contrast, has been compounding on timescales of decades. That mismatch means a species can find itself holding tools capable of planetary-scale consequences while still running on judgment, cooperation, instincts, and institutions that evolved to handle the much smaller stakes of small group survival on the African savanna, not global coordination problems involving billions of strangers and machines more capable than any individual human mind. That gap doesn't stay open forever. Either a civilization builds the coordination and wisdom to close it, or the gap itself becomes the mechanism that ends the experiment. Either way, it's temporary. By definition, confined to a relatively narrow stretch of a civilization's history right around the point. Technological capability first outpaces institutional maturity, which is exactly the shape of window, the great filter. In its late position form, would need to exist. This isn't purely abstract, either, and it's worth grounding in one specific, well-documented moment from humanity's own recent history. rather than leaving it as pure statistics. On the 26th of September, 1983, at the height of Cold War tension between the two nuclear superpowers, a Soviet early warning satellite system reported that the United States had launched a wave of intercontinental ballistic missiles. The duty officer that night, an engineer named Stanislav Petrov, had only minutes to decide whether to report the warning up the chain of command, a report that, understanding protocol, would likely have triggered a retaliatory launch. He judged the alarm implausible, reasoning that a genuine first strike would have looked different, and chose to wait rather than escalate. The satellite system, investigators later confirmed, had mistaken sunlight reflecting off high-altitude clouds for missile launches. It was a false alarm, caught by one person's judgment on one ordinary night decades ago. And it's a concrete, undisputed illustration of exactly the gap this chapter has been describing. A civilization holding tools capable of ending itself, operated by systems and institutions that, on that particular night, came within one person's reasoned hesitation of a catastrophic failure. Multiply a night like that across enough decades, enough nuclear-armed states, enough newer and less battle-tested technologies, and Ord's estimated odds stop feeling like an abstraction and start feeling like the ordinary background hum of the century humanity is currently living through. Sit with what that means inside the framework Chapter 4 built. If even a modest fraction of technological civilizations across the galaxy face odds anywhere close to those applied repeatedly across their own critical century of development, and if that century of maximum vulnerability sits at roughly the same stage every technological species would pass through, the stage where you've developed enough power to end yourself before you've developed enough wisdom or coordination to manage that power safely, then self-destruction alone, with no aliens, no predators, no external villain of any kind, becomes a genuinely sufficient candidate for the Great Filter. Not a certainty, a candidate that fits the shape of the evidence uncomfortably well. It would filter almost everyone at almost the same stage, which is exactly the kind of late, close to us position the numbers from Chapter 4 were already leaning toward before this chapter named a single specific mechanism. That's the sober version. And it deserves to stand entirely on its own, because it doesn't need help from fiction to be unsettling. It's built from published risk analysis, from researchers whose job is specifically to estimate these odds as carefully as the available evidence allows, applied to a species, ours, that is currently living through exactly the century those estimates are about. Now, separately, and clearly labelled as separate, there is a second dark candidate that has become extremely well known, not because scientists proposed it as a testable hypothesis, but because a novelist turned it into one of the most gripping ideas in modern science fiction. In 2008, the Chinese author Liu Cixin published a novel called The Dark Forest, the second book in a trilogy that began with the three-body problem, translated into English in 2015. Inside that novel, a character works through a piece of reasoning that has since become known, even outside the book's own readership, as the dark forest hypothesis. Imagine the galaxy as a dark forest at night, full of hunters, where every civilization is armed, resources are finite, and, critically, there is no way to reliably know in advance whether a civilization you've just detected is friendly or hostile, or whether it will remain friendly as it grows in power. Under those conditions, the novel's logic goes, the only rational move for any civilization that notices another one is to destroy it immediately, before it can grow into a threat, and to otherwise stay as silent and hidden as possible, so that no one else does the same to you first. Announce yourself in this scenario, and you paint a target on your own civilization that never comes off. It is a genuinely brilliant piece of storytelling logic, built on real game-theoretic bones. The same kind of reasoning that shows up in serious academic work on trust, deterrence, and cooperation under uncertainty. The underlying structure will be familiar to anyone who has studied the classic prisoner's dilemma from game theory or the decades of academic work on nuclear deterrence during the 20th century's standoff between nuclear powers, where each side's rational strategy depended heavily on what it assumed about the other side's intentions, and where uncertainty about those intentions was itself treated as a dangerous, destabilizing force. Liu Cixin's novel takes that same structural logic and scales it up to a galactic stage, where the players are entire civilizations. Communication delays are measured in centuries or longer because of the speed of light. And there's no shared authority, treaty, or history of prior contact to build trust on at all. Conditions that, if they held, actually would make cooperation harder to sustain than it was even at the height of Cold War brinkmanship. That's what makes the idea so compelling as fiction. It isn't arbitrary paranoia. It's paranoia with an internally consistent, almost mathematical logic behind it. But it is worth being completely explicit about what it is and isn't. It is a thought experiment embedded in a work of fiction written to serve a novel's plot and themes. It has not been observed. It has not been tested. It does not rest on any measurement, survey, or piece of physical evidence the way the earlier chapters of this hour do, treating it as though it carries the same evidential status as the Great Filter, or as published existential risk research would be exactly the kind of overclaim this investigation has been trying to avoid since the opening chapter. It belongs in this hour because it's become part of how a huge number of people now talk about this topic, and pretending it doesn't exist would leave a gap in the conversation. But it belongs here labelled honestly, as a powerful metaphor for a real category of risk, not as a scientific finding in its own right. And here's the part worth sitting with before moving on, because it actually makes the fictional idea more interesting rather than less, once you see how it relates to the sober one. You do not need a galaxy full of armed, paranoid hunters for the silence to make sense. You do not need anyone, anywhere, actively destroying anyone else. The published, peer-reviewed candidate, a species developing the capacity for large-scale self-harm well before it develops the wisdom, coordination, or institutions to survive that capacity, is entirely sufficient on its own. No predators required. No malice required. Just a narrow window, repeated across every technological civilization that ever reaches it, where power and caution arrive badly out of sync. The Dark Forest gives that same basic danger a face and a villain. The Great Filter, in its sober academic form, doesn't need one. It only needs time, technology, and the ordinary difficulty of getting the second thing to keep pace with the first. It's worth pausing, too, on why the fictional version of this idea spread so much further and so much faster than the sober academic one ever did. Existential risk papers live in journals, policy briefings, and the occasional widely discussed book. A well-told story reaches millions of people who will never read any of them. That asymmetry is exactly how a compelling but unverified idea can end up feeling more authoritative in casual conversation than research that's actually been reviewed, tested, and debated by specialists. Not because the fiction is dishonest, but because narrative is simply a far more efficient way to spread an idea than a peer-reviewed paper is. Keeping that asymmetry in mind is part of what it means to use fatos verificables. Honestly, noticing when an idea's popularity and its evidential weight have quietly come apart from each other, and correcting for it deliberately rather than letting the more vivid version simply win by default. That distinction matters for how you should feel leaving this chapter. A universe full of hostile hunters is frightening in a way that at least has an external shape to it. A threat you could, in principle, imagine defending against, hiding from, or someday negotiating with. A universe where the filter is simply us, and specifically this exact stage of us, offers no external enemy to identify, no obvious hiding strategy, and no one to blame but the gap between what a civilization can build and what it has learned to responsibly manage. If the numbers from chapters 1 through 5 are right, and if the filter really does sit late rather than early, this is very likely the more accurate of the two dark readings, and it is, if anything, the harder one to sit with, precisely because there's no villain in it. Everything so far has treated the Great Filter as an abstract argument, a logical requirement, a shape the evidence has to fit somewhere. This chapter does something more specific and, honestly, more personal. It takes the actual sequence of steps between raw chemistry and a technological species and asks, as carefully as the evidence allows, which of those steps in our own history look like they were easy, and which ones look like they were almost impossibly hard. Because if we can find a step in our own past that looks like the rare one, that's evidence, however tentative, that the filter sits behind us. And if every step in our past looks comparatively easy, with nothing unusual behind us to explain why so few others made it this far, that pushes the weight of the argument forward toward a filter we haven't reached yet. Start at the very beginning, the origin of life itself, chemistry becoming biology. Chapter 1 already covered the headline version of this, that some of the earliest chemical evidence many scientists interpret as biological activity appears within the first few 100 million years after Earth became capable of holding liquid water at all. Read that fact through the lens of this chapter, and it starts to look like evidence, tentative but real, that this particular step isn't the hard one, a process that gets underway almost as soon as the conditions allow it. On the very first planet we have data for, doesn't look like a once-in-a-galaxy fluke. It looks like chemistry doing something it's inclined to do whenever it gets the chance. Move to the next major transition, and the picture changes completely. For roughly the next 1.5 to 2 billion years after life first appeared, Earth's biology remains simple, single-celled organisms without the internal complexity that every plant, animal, and fungus alive today depends on. Simple, though, doesn't mean uneventful. Somewhere around 2.4 billion years ago, a group of microbes called cyanobacteria, which had evolved the ability to produce oxygen as a byproduct of photosynthesis, triggered what geologists now call the Great Oxidation Event. Oxygen, essentially a poison to most of the anaerobic life that had dominated Earth until then, began accumulating in the atmosphere for the first time, devastating huge swaths of existing biology, disrupting the planet's chemistry, and even helping trigger severe, prolonged global glaciations by stripping out atmospheric methane. It's worth sitting with the irony for a moment, because it echoes forward all the way to Chapter 6 of this hour. The first large-scale, planet-altering environmental catastrophe in Earth's history wasn't caused by a technological civilization at all. It was caused by simple, ordinary bacteria doing nothing more sophisticated than what their own biology compelled them to do. And it nearly cost the planet's biosphere everything in the process, life reshaping its own environment catastrophically, faster than most of that environment's inhabitants could adapt. Turns out to be a pattern, with roots reaching back billions of years before humans arrived to repeat it on a technological scale. Researchers place it roughly between 1.8 and 2.7 billion years ago. Something else happened that many biologists now regard as one of the strangest and most consequential events in the entire history of life on this planet. Two entirely separate, simple single-celled organisms merged, one becoming absorbed inside the other, in a partnership so successful and so total that the two effectively became one new kind of cell. The absorbed partner became what we now call the mitochondrion, the structure that still exists inside nearly every complex cell in your own body, generating the energy that everything else depends on. This merger is what produced what biologists call the eukaryotic cell, the complex, internally structured cell type that all animals, plants, and fungi are built from. Here's the detail that makes this transition look like a genuinely strong candidate for a hard step in the Great Filter sense. According to the geneticist and biochemist Nick Lane, one of the leading researchers on the origin of complex cells, the best current evidence points to this merger having happened only once, a single successful event, 4 billion years into the history of life on Earth, from which every complex organism that has ever existed, including every animal, is descended. Not dozens of independent origins that were then outcompeted by one successful lineage. As far as the evidence currently shows, one origin, one success, out of what should have been countless opportunities for it to happen, across billions of years of simple cells living side by side with the ordinary bacteria that occasionally do get absorbed by one another without any lasting merger resulting. If that reading holds up, and it remains an active, debated area of research, not a settled consensus, it would mean humanity's own evolutionary history contains exactly the kind of astronomically rare, one-off event the Great Filter argument predicts should exist somewhere along the chain. A step so difficult that it may have needed billions of years and something close to universal luck to clear even once. On the one planet we can actually check. Notice what that would mean for the position of the filter. If this really is the hard step, it would mean the filter sits behind us. We already have complex cells. We already cleared, by pure fortune, the step that this line of research suggests might be the genuine bottleneck. Everything after that, the jump to multicellular bodies, the evolution of nervous systems and intelligence, even the development of technology would, under this reading, be comparatively easy, evolutionary business as usual, rather than a second miracle waiting to strike us down. That's the version of this hour's argument that lets you exhale, but the honest version of this chapter can't stop there. Because the eukaryotic cell isn't the only candidate, and there's a second pattern in the evolutionary record that cuts in the opposite direction. Multicellularity, the step from single complex cells to bodies made of many cooperating cells, turns out, unlike the origin of the eukaryotic cell, to have evolved independently many separate times across the tree of life. In algae, in fungi, in several entirely different animal lineages. A transition that happens independently, repeatedly, in unrelated groups is exactly the signature of an easy step. Not a hard one. Nature finding the same solution over and over because the door isn't actually that narrow. That fits the optimistic reading. Another step behind us, cleared with room to spare. Intelligence and technology are where the record gets genuinely hard to interpret. And this hour owes you honesty rather than false confidence here. Recognizable intelligence, in the sense of complex problem-solving and social learning, appears to have evolved independently in multiple lineages. Not just our own, including certain birds and cetaceans, which hints that it too might not be the rarest step. But technological civilization, in the specific sense of a species building tools sophisticated enough to alter its environment on a planetary scale and broadcast its presence beyond its own atmosphere, has so far happened exactly once, in the roughly 4 billion year history of life on this one planet. And it has existed for a period so brief, a handful of centuries, that it barely registers on any of the timescales this hour has been working with. We simply don't have enough data, from a sample size of 1, to know whether this step is easy, and we just haven't had time to see it happen twice. Or whether it's staggeringly rare and we are, right now, living inside the one lucky instance. There's a deeper problem hiding underneath that sample size of 1 difficulty. And it's worth naming even though it complicates the tidy version of this argument, because pretending it away would be its own kind of dishonesty. It's a form of reasoning philosophers call observation selection, the simple fact that we can only ever be having this conversation from inside a history where our own lineage didn't already go extinct at any of the steps discussed so far. Every one of those steps, the origin of life, the merger that produced complex cells, the jump to multicellular bodies, the rise of intelligence, had to go a specific way for anyone to exist afterward, capable of asking whether that step was rare. A species standing on the far side of a genuine bottleneck, looking backward, will always see a chain of successes leading up to itself. No matter how astronomically unlikely each individual link actually was, simply because failed chains don't produce anyone to look back and count the odds. This doesn't undo anything in this chapter. It's not a reason to distrust the evidence about the eukaryotic cell or multicellularity, but it is a reason for real humility about how confidently anyone, including this hour, can read our own past as evidence about how common life in general actually is. Because the vantage point we're reasoning from was never a neutral one to begin with. We are, by definition, looking backward from the one branch that worked. That same observation selection caution cuts the other way too. And this is the detail worth sitting with longest before this chapter ends. It applies to the future exactly as much as it applies to the past. Every civilization that has ever asked a version of Fermi's question has, necessarily, been asking it from a position of not yet having been filtered out, which means the mere fact that we're here, alive, capable of worrying about this, tells us comparatively little on its own about how dangerous the road ahead actually is. A civilization standing safely on the far side of its own hard step feels exactly the same from the inside as a civilization standing right before it. Neither can feel the difference in advance. That is precisely why this hour has leaned so heavily on external evidence. The silence itself, the searches, the timescales, rather than on the comforting but unreliable feeling of, well, we've made it this far. Making it this far is not evidence of safety. It's simply the minimum precondition for being able to ask the question at all. There's one more piece of research worth including here, because it comes from the same source as the framework this entire hour has been built around, and it approaches the timing question from a completely different angle than anything covered so far. In 2021, Robin Hanson, the same economist behind the original Great Filter essay in Chapter 4, returned to this problem with a group of co-authors and a new observation. If reaching a stage like ours genuinely requires clearing several difficult, low-probability steps in sequence, basic statistics says that the further back in the universe's history you look, the rarer it should have been for any civilization to have finished that sequence yet. Run the math forward, and it implies something odd about humanity's own position, that a civilization appearing this early in the universe's habitable history, on this particular timeline, is itself a little bit surprising, almost as surprising as the silence is. Their proposed resolution links directly back to the Great Filter. If there really are other civilizations out there that expanded aggressively enough to become what the paper calls grabby, loud, visible, physically spreading through space, then those civilizations would tend to fill up and effectively claim their surrounding volume of the universe, making it statistically less likely for a new civilization like ours to arise nearby later, simply because the available room to appear on time would already be taken. Humanity appearing this early, under that model, becomes modest evidence that expansive, galaxy-filling civilizations are rare enough, or slow enough, that they haven't yet claimed our particular neighborhood, which is a subtly different, and in some ways more hopeful, angle than anything the earlier chapters offered, even though it's built on the same underlying suspicion that loud, visible civilizations are hard to become in the first place, which brings this chapter to the reclassification the entire hour has been building toward. The Fermi Paradox, treated honestly, is not a trivia question about extraterrestrial biology. It's a live diagnostic test being run on our own species, using evidence we are still in the process of gathering. Some of it, like the single origin of complex cells, pointing tentatively toward a filter already behind us. Some of it, Like the total silence from a galaxy of billions of candidate worlds, despite ingredients and timescales that should have produced exceptions, pointing toward a filter that might still be ahead. Both readings are consistent with everything gathered across this hour. Neither one is proven. And that, uncomfortably, is the actual, current, honest state of the science. Not a confirmed answer, but a genuinely unresolved test. With humanity as one of the very few data points anyone has ever been able to examine from the inside. There is, however, one asymmetry in the evidence worth naming plainly before this hour closes, because it's the closest thing to a verdict the current data actually supports, if the hard step really were safely behind us. Cleared. Done. No longer a live risk. You would still expect the galaxy to look at least somewhat less silent than it does, because plenty of other civilizations, having also cleared that same early bottleneck by the same odds that let us clear it, should be visible by now. Expanding, broadcasting, building, the fact that the silence remains this total, even after 5 chapters of finding the earlier steps easier and more common than a species in 1950, or even in 1996, would have guessed, is itself a small but real piece of evidence, nudging the argument later, not earlier, toward a filter still in front of us, rather than safely in the past. Small, not conclusive, but real and leaning in the direction this hour's title warned you about from the start. Picture that lunch table again, in the New Mexico desert, in the summer of 1950. 4 men walking to eat, talking about flying saucers and disappearing trash cans, when one of them asks a question he never bothered to write down, because at the time it probably felt like a joke, or at most a mildly interesting puzzle to chew on between bites. Where is everybody? Nobody at that table could have known what the question would turn into. They didn't have Drake's equation yet. That was still 11 years away. They didn't have a single confirmed planet outside our own solar system, let alone billions of candidates. They didn't have Hansen's Great Filter, or Bostrom's formal definition of existential risk, or a documented near miss from a Soviet control room, or a 72-second radio anomaly that would still be unexplained half a century later. All they had was a hunch that the universe's numbers didn't add up to the silence around them. A hunch that would outlive the man who voiced it by more than 70 years. Get formalized by other people's math, get tested by other people's telescopes, and eventually arrive at an answer that isn't really an answer at all, closer to a verdict still being handed down, one piece of evidence at a time, with humanity itself sitting in the position of both the jury and the defendant. Here is what this hour has actually established, stated as precisely as the evidence allows, without inflating it past what it can support. The ingredients for life appear to be common, likely numbering in the billions of candidate worlds across our galaxy alone. The timescales available are vastly more than sufficient for even a single, successful, modestly expansive civilization to have become visible by now, and the strongest counterarguments to that math soften the tension without erasing it. Every independent method of searching, radio signals, infrared heat signatures, the underlying population mathematics of colonization itself keeps returning the same result: nothing. And when that pattern is run through the logical framework built specifically to make sense of it, the honest reading is not that no filter exists. It's that a filter clearly does exist, and the accumulating weight of what makes the early steps look easier keeps shifting the most likely position of that filter later in the sequence, closer to where we now stand, rather than safely behind us. That is the darker meaning this hour's title promised, and it deserves to be stated in its plainest form, without softening it into a shrug. The silence across our galaxy is most consistent, given everything currently known, with civilizations reliably failing at or near the exact stage of development humanity has just reached. Not from alien predators, not from cosmic accident, but most plausibly from the same gap Nick Bostrom named and Toby Ord tried to measure. The gap between building the power to end yourself and building the wisdom to not use it. Not a certainty, a weight of evidence, leaning in one direction from a species that only gets to run this particular experiment once. Say plainly what this hour is not claiming, because the difference matters. It is not claiming humanity is doomed. It is not claiming a specific date, a specific mechanism, or a specific outcome. Ord's own numbers, stated earlier in this hour, put the chance of surviving this century at something closer to 5 in 6 than 1 in 6. Good odds, by any reasonable standard, just not certain ones, and not odds that improve automatically with the passage of time alone. What the evidence gathered across 8 chapters actually supports is narrower and in its own way more useful than either doom or reassurance. That the silence humanity has been straining to explain since 1950 is not a mystery about somebody else. The most likely reason nobody else is visible is not a story about aliens at all. It's a story about a threshold every technological species apparently has to cross on its own, without a guide, and about which side of that threshold any given civilization, including the one asking the question, actually turns out to be on. None of that is a prophecy. The evidence that pushed the filter's likely position later is also evidence that we can see the shape of the danger clearly enough to name it, measure it, and, at least in principle, do something about it, which is a very different situation from a species stumbling toward the same fate blind. Every one of the researchers cited across this hour, from Hansen to Bostrom to Ord, built their work on exactly that premise. Not a form of giving up on it. What doing something about it actually looks like is deliberately left open by every serious piece of research this hour has drawn on. And that's not an evasion. It's the honest state of a genuinely unsolved problem. It isn't a single policy, a single technology, or a single decision. The researchers cited across this hour tend to converge on a narrower, less satisfying but more defensible point, that the gap between capability and wisdom Chapter 6 described isn't fixed in place, the way a law of physics is. It's closed, when it gets closed at all, by exactly the kind of unglamorous, unfinished work civilizations already have some practice at. Building institutions that outlast any single decision maker, developing the ability to evaluate a new technology's risks before deploying it at scale rather than after, and maintaining enough coordination to act on a slow-moving danger before it becomes an unavoidable one. None of that guarantees anything. It's simply the difference between a species that has identified its own most dangerous century and a species that hasn't. An identification, however uncomfortable, is the only step in this entire process that is actually within reach today. Think back, for a moment, across everything this hour actually gathered, rather than everything it merely speculated about. A radio telescope in Ohio caught 72 seconds of something in 1977 that has never repeated and never been explained, a genuine anomaly that still isn't the exception. A filled galaxy should be producing constantly. A catalogue of nearly 100 proposed explanations, assembled by a working scientist in 1983, has been quietly worn down, chapter by chapter, to a small handful that survive contact with the evidence. And even the survivors, honestly examined, keep pointing the same direction rather than offering genuine comfort. A hypothesis that we're simply being watched, left alone on purpose, turned out to require an almost impossible unanimity across a galaxy's worth of independent civilizations to actually work. None of these threads, on their own, proves anything. Together, they stopped behaving like scattered curiosities somewhere around Chapter 4 and started behaving like independent measurements of the same underlying fact, converging from different directions on the same uncomfortable answer. So the honest place to leave this is not with despair, and not with false comfort either, but with the question restated one final time, now carrying the full weight of everything gathered to answer it. 70-some years ago, at a lunch table in the desert, a physicist asked where everybody was, half joking, and never got an answer in his lifetime. We still don't have one. What we have instead is a sharper, colder, more specific version of his question, aimed now not outward at the stars but back at the species, asking it, not, where is everybody, but whether we are going to become one of the ones who made it through, or one more silence added to a galaxy that already holds far too many.